books mainly consist of definitions, axioms and postulates, where definitions are explanations of geometry with certain undefined terms which are acceptable. Now, what about axioms and postulates? Euclid assumed certain properties which were not to be proved, for they are actually obvious universal truths. He divided them into two types. They are axioms and postulates. He used the term postulate for the assumptions that were specific to geometry. Axioms, also called as common notions, are assumptions used throughout mathematics and not specifically linked to geometry. Let's see some of Euclid's axioms. Things which are equal to the same thing are equal to one another. This could be applied to plane figures. Suppose the area of a triangle is equal to the area of a square. The area of a circle is also equal to the area of the square. Then the area of the triangle is equal to the area of the circle. Please note that only the magnitudes of the same kind can be compared and added, but magnitudes of different kinds cannot be compared. For example, a line cannot be compared to a rectangle. The next one is, if equals are added to equals, the wholes are equal. Suppose the amount of rice in these two bowls, say A grams and B grams, are equal. Let's add 10 grams to each bowl. The resulting amount will be A plus 10 grams and B plus 10 grams respectively, which are both equal to each other. Now let's see the next axiom. If equals are subtracted from equals, the remainders are equal. If 10 grams were removed from the two bowls of equal amount of rice, A grams and B grams, the result will be A minus 10 grams and B minus 10 grams respectively, which are equal to each other. The next one is, things which coincide with one another are equal to one another. Consider two triangles. If we place one over the other and find that they coincide with one another, then the two triangles are equal to each other. The next axiom is, the whole is greater than the part. Consider a circle. It is divided into 4 parts. Now if we consider the blue part, which is 1/4 of the whole circle, we can say that the whole circle is greater than this blue part. The next one is, things which are double of the same things are equal to one another. Consider two lines AB and PQ, both of 5 cm, so equal to each other. Suppose we double the lengths of both lines. Both the lengths will be 10 cm, which are equal to each other. The last one is, things which are halves of the same things are equal to one another. Consider the same lines AB and PQ. If we remove half of the lengths of both lengths will become 2.5 cm, which are equal to each other. From these axioms, we can further deduce and prove more statements related to geometry. And if it is impossible to deduce from these axioms, contradicting any axiom or previously proved statement, then they are called consistent. So when a system of axioms is given, it needs to be ensured that the system is consistent. Now let's see a few examples how Euclid used his axioms for proving some of the results. In the figure, if AC equals BD, then prove that AB equals CD. It is given that AC equals BD. Let's see what are AC and BD from the figure. AC is AB plus BC and BD is BC plus CD. According to Euclid's axiom, when equals are subtracted from equals, remainders are also equal. So subtracting equals, that is BC, from LHS and RHS of the above equation, we get AB plus BC minus BC equals BC plus CD minus BC. That is AB equals CD. Hence, we have proved the statement. Let's see another problem. If A plus B equals 5, then prove that A plus B plus C equals 5 plus C. Given A plus B equals 5. According to Euclid's axiom, if equals are added to equals, the wholes are equal. Adding C to LHS and RHS of the above equation, we get A plus B plus C equals 5 plus C, hence proved. So we can conclude that Euclid's axioms are assumption of actually obvious universal truths which are applicable not only for geometry but also for the entire mathematics. And it is consistent if it is impossible to deduce from these axioms a statement that contradicts any axiom or previously proved statement.